Hey class, welcome to Module 10. In this module we're going to be studying radical functions. And our essential question for the module is how can you use radical functions to solve real-world problems? So of course that's always our focus in math. That's why we study math, is to solve problems. In the first lesson we're going to take a look at the inverses of simple quadratic and cubic functions, which actually result in some radical functions. And our essential question will be, what functions are the inverses of quadratic functions and cubic functions, and how can you find them? So I just mentioned the word inverse, and we've studied about some inverse functions. We mainly focused on inverses of linear functions, but remember the word inverse we kind of related to reverse, and what we really mean by an inverse is we're looking at the situation from the other variable's perspective. And so what does that look like from the other perspective? So if we were looking at, say, a quadratic function, and what would be the inverse of quadratic? Well, if you remember, a quadratic function is has an exponent of 2, so it's a squared function. And if you think about what the inverse of squaring something is, or what undoes squaring, we think of square rooting. So that a square root is a radical, and that's actually what our module is about radical functions. So the inverse of a quadratic function will be a square root function, and we'll also look at the inverse of a cubic function, which will be a cube root function. And we're going to start off with finding and graphing the inverse of a simple quadratic function. So the inverse of a quadratic function is, as I just mentioned, a square root function, which is a function whose rule involves the square root of x. Now the parent square root function is the square root of x. And I'm going to take a real quick second to sketch and show you what that looks like. So if I wanted to graph the square root of x, and I started thinking about what values I could substitute in for x, I think right away that the smallest number I could put in there is 0, because remember we can't deal with negative radicands, as that would give us imaginary numbers. But we could start off by putting 0 in, and if I substituted in a 0 for x, I would get a 0 out. So that point would be right here at the origin, which is pretty characteristic of the parent functions. They always cross through the origin. If I were to put 1 in there for x, and I took the square root of 1, I get 1. So 1, 1 would be a point on my graph. Now, also negative 1, but that would be a separate function in itself, though. So we're really focusing on the positive square root of x. And so we want to just take the positive roots. And so if the next one I think is kind of convenient would be probably not to put in 2 or even 3, but to substitute in 4, because the square root of 4 is 2. And then maybe even 9, because that's another perfect square. So 4, 5, 6, 7, 8, 9. If I substituted in 9 for x, the output when I took the square root would be positive 3. And so I get a curve that looks like this. Now that's not really surprising, because if you think about what a parabola looks like, so you know a parabola looks like this, and inverses are supposed to be reflections of each other over the line y equals x. And if you were to just take one branch of that parabola and reflect it over the line y equals x, so like if you just focused on the right hand side where your input values would be positive or 0, and you just took just that little piece of the graph right here and you reflected it over the line y equals x, you would get this graph. So this is the parent function, the square root of x. So in our first example, we're going to look at restricting the domain of each quadratic function and finding its inverse. And then we're going to confirm the inverse relationship using composition of functions. Well, actually, we're not going to do that part because that's something we have yet to talk about. At least we haven't emphasized too much. So we're just going to check it graphically, and then we'll talk more about what composition of function is later. So first of all, this original function, if we look at that quadratic, I mean, you think about, we know transformations of quadratics, that 0.5x squared, that seems to be a vertical compression of a half of the parent function. So look, if I wanted to graph that function, start off, I know I could make a little table of values, or I could just plug in some points. So if I say plugged in 0, 0 squared is 0 times a half is still 0. But say I plugged in 1, so 1 squared is 1, and then 1 times a half is a half, so that would give me a point, like, say, right about here. And then if I plugged in -1 squared is also 1, and then take half of that would put me at -1 and then a half. So again, oops, can't get that. There you go. And then I could say plug in 2. So if I plugged in 2 squared would be 4. Half of 4 is 2, so that would give me a point here. Get this side of the parabola. You can definitely see that compression vertically because normally those points would be at 1, 1 and 2, 4. And then on the other side as well, if you plug -2 in, you'd get +2 out because -2 squared is 4 and half of that is 2. So that gives us a point right here. And that's my other side of my parabola. But we said we were going to restrict our domain. And so what I meant by restricted domain is we're only going to substitute in positive values of x and 0. So if we make the domain be x such that x is greater than or equal to 0, then we wouldn't have this other side of the graph. We would just have the right-hand side when we plugged in positive numbers. So we're just going to go with the restricted domain version of this graph, which is just this piece of that parabola. Now next we want to write the inverse, and remember that when we talk about inverse, we want to reverse the variables, and that's really the first step we take. So f of x is really like saying y. So if we were to switch the places of x and y, this would look like x is equal to 0.5 y squared. And now we want to solve for y so that we can get it back in that function notation. So the first thing we'd have to do is divide both sides by 0.5. Well, dividing both sides by 0.5 is like multiplying both sides by the reciprocal, which would be like multiplying by 2. So this is really 2x. And that equals y squared. And then to solve for y, we want to undo the squaring, so we're going to go ahead and square root both sides, giving me y is equal to the square root of 2x. And then if I wanted to write it in function notation, remember we then replace y back with the function, but we use this to the -1, which is read f inverse of x, and then equals the square root of 2x. So now we're going to go ahead and graph that. So I'll make a little table for that. And when I think about the numbers I can possibly put in, the smallest number I could possibly put in is 0. And that's because, well, first of all, we're restricting the domain, but if I plugged in anything like, say, a negative number in there, it's going to be a negative radicand. So if I substitute in 0 and I multiply by 2, I get 0. The square root of 0 is 0. If I put in, say, 1, and I multiply it by 2, that's 2, which then the square root of 2, that's not a nice number, so I'm going to go ahead and put in 2 instead. Just kind of got an idea this will work better. So 2 times 2 is 4, the square root of 4 is 2. Again, we're focusing on the positive root. And then probably the next best one would be to put in, say, 8, because 8 times 2 is 16, the square root of 16 is 4, so that gives me some nice output numbers, so I just picked values I thought would work nice here. And if I were to go ahead and plot these points now, on the graph, I'd have 0, 0, that's a shared point, and 2, 2, over 2, up 2, oh, look, that's another shared point, and then 8, 4, so over 8, up 4. So maybe if I had a point in between 0 and 2, that would help, but what's going to happen is since this is a curve, it's like that branch on its side, it's going to look like this. So that's, for sure, looks like it's the reflection of this one side of that parabola. And we know that if they are, in fact, inverses, that if I were to draw this line in here at y equals x, that should be a reflecting line, and you can clearly see that that is the case. So again, my domain here is x such that x is greater than or equal to 0. And I think for obvious reasons, if we were to put in anything below 0, we're going to be having a radicand that's negative. Okay, so let's take a look at another example. So example B is f of x is equal to x squared minus 7. Now, you recall that is a quadratic. That's like a parent function quadratic, base parabola, that is shifted down 7, because that's a slide down 7. So that's going to just be that standard parabola, but instead of the vertex being at 0, 0, it's going to be at 0, -7, so that's going to be right here. And we're going to have those typical points that we normally have on a parabola, parent parabola, which is when you go to the right 1, you go up 1, because if you plugged in 1 on a base parent parabola and squared it, you'd get 1. When you plug in 2, you'd get 4, and so on. So basically I'm just going to kind of recreate those points. You could also just plug into the original equation, but it's just a little more complicated. So I just kind of pretend like this is my new origin right there at the vertex. So I know that this is what that parabola is going to look like. It's going to continue on this trend. It looks like this. But then again, what we really want to do is just focus on this right-hand side, which is when the x values are positive. And so I'm going to go ahead and just graph that part of it. And so again, we're just really restricting the domain of the original to have it only be x greater than or equal to 0. So now I'm going to write the inverse. So again, we're going to replace f of x with y, and then we're going to switch those up. And when I do that, that's going to give me x is equal to y squared minus 7. And so then I want to go ahead and solve for y. So step 1 is I'm going to want to bring this 7 to the other side. So I got to isolate that y squared. So that would be x plus 7 equals y squared. And then of course I'm going to take the square root to undo that square. And that gives me y is equal to the square root of x plus 7. But remember, I want to use that function notation, so I'll use inverse f of x, so f inverse of x is equal to the square root of x plus 7. And so if I wanted to graph that, the smallest possible number I could put in there to graph that thing is what would make that radicand 0. So that means I don't want to put in anything that's smaller than -7. So if I wanted to restrict my domain so that I don't get any imaginary numbers, I'd have to say in this case that x is such that x cannot be less than or equal to -7, so it's got to be greater than or equal to -7. And that's where I'm going to start with my table. So I'll put in a -7, maybe a -8, and so on. Sometimes I kind of manipulate the numbers I'm going to use just because I know that they work well. So if I plug in -7 in, -7 plus 7 is 0, the square root of 0 is 0, so I'll have a point right here at -7 and 0. So that's right here. And that makes sense because we know that these graphs are going to be reflections of each other, and that means that if we kind of compare to this line, this y equals x, this line that will split right through the first and third quadrants, whatever the y-intercept is on the parabola should be the x-intercept of this square root graph, and it is. So then when I put -8 in, -8 plus 7 is, oh, I'm sorry, I didn't mean to put -8. I just think that. -6, excuse me. That was silly. -6. -6 plus 7 is 1, and the square root of 1 is 1. So -6 and 1, which is right there. And then maybe I'll skip up to where I can make that radicand 4. So let's say I made it -3. And again, I'm just kind of manipulating this so I have nice square roots. So -3 plus 7 is 4, square root of 4 is 2. And so -3, I could put a point at 2, and so on. And then, like eventually, well, the next perfect square is 9, so how I would get that is I would have to put in something that's going to make that 9, which would be 2. So if I plug 2 in for x, that's 9 is the radicand, square root of 9 is 3. So I could even put that in over 2 and up 3. And that gives me just one more point. And as I graph this, it's going to go like that, continue. And of course my parabola down here, if I had extended out a little further, would go like that. And you can see that these are reflections of each other. So here's my inverse, and here's the restriction on my domain. And you can clearly see that the graphs are reflections of each other. Now we talked a little bit about, I said something about composition, and so just composition of functions basically just means if you take one of the functions and you substitute it in for that independent variable x in the other, it should, if these are inverses of each other, they should basically cancel out all the operations and simplify down to just x. So like I'll show you one direction of that. If I took and in the square root of x plus 7, if I took that original function, this x squared minus 7, and I put it in place of x in that function, it would look like this. In place of x, I'd put in x squared minus 7, which is the original function, but then there's this plus 7. So then when I end up simplifying that, the negative 7 and 7 cancel out. This is just the square root of x squared, which is then just x. And if you did that the opposite direction as well, then, and you could confirm then if these two functions undo each other, then they're inverses. So that's what we meant by a composition of functions. So we're going to go ahead and save the your turn questions for class. And so we're just going to go ahead and turn the page and take a look at an application problem. So you may remember when we studied inverses with linear functions, we really approached things differently when we were dealing with real-world problems. So in general, with real-world problems, we do not switch the variables as we did in those prior examples. In those prior examples, x and y are really sort of arbitrary variables that we chose. But in real-life problems, we usually pick variables that are specific to the situation. And so that when we switch those variables around, we completely change the meaning of things. So instead what we do is we just simply solve for the other variable. So for instance, in this scenario, we're asked to find the inverse of each of the quadratic functions, use the inverse to solve the application. And so it says the function d of t is equal to 16t squared gives the distance d in feet that a dropped object falls in t seconds. Write the inverse function t of d to find the time t in seconds it takes for an object to fall a distance of d feet. Then estimate how long it will take a penny dropped into a well to fall 48 feet. So it says the original function, d of t equals 16t squared, is a quadratic function with a domain restricted to t greater than or equal to 0. Because, of course, negative time wouldn't make sense. So now they want us to find the inverse. So again, we're going to start off with the original, which is the d of t equals 16t squared. But I'm just going to drop that function notation and just call it d instead. And so now what I want to try to do is I want to instead solve for t. I'm not going to switch the variables like I usually do, because again, switching t and d really will change their meanings. T represents time and d represents distance, so we want to maintain those meanings by not switching them. But now to solve for t, I'm going to divide by 16, and that's going to leave me my t squared, which then I could go ahead and take the square root of both sides, and that'll cancel out the squared, leaving me with t is equal to the square root of d over 16. Now if we wanted to, we could actually split that numerator and denominator up and actually take the square root of the 16. So another way to write this would be to write it as the square root of d over 4. But not all the time will this denominator be a perfect square. So, usually as a rule we just kind of leave it like that with the whole expression under that radical. But again, it is also okay if it is a perfect square that you can go ahead and take the square root of that denominator. So for just because to be consistent with when we don't have perfect squares, we'll go ahead and leave it like this. And then we're going to go back to that function notation, but instead of it being d of t, now it's t of d. So it's time as a function of distance. And now we have a function that we can use and to estimate for our given situation. So we want to know the time now when the distance is 48, and that just means we're going to plug 48 in for d and find that value. So that really means we're taking the square root of 48 divided by 16, which is 3, and the square root of 3 is approximately 1.7. And remember, we're talking about time here, and in this case it was given in seconds. So it's time in seconds, so 1.7 seconds for that penny to fall the 48 feet into a well. And then if you drop that penny in the well, maybe it's a wishing well, and you can make a wish. Okay, let's look at one more real-life example with a quadratic equation. So the function e of v is equal to 4v squared gives the kinetic energy E in joules of an 8 kilogram object that is traveling at a velocity of v meters per second. So again, we know that E is energy in joules, v is velocity in meters, so it's always good to kind of identify what the variables represent. Write and graph the inverse function v of E to find the velocity v in meters per second required for an 8 kilogram object to have a kinetic energy of E joules. Then estimate the velocity required for that object to have a kinetic energy of 60 joules. So first we're going to write the function by doing the inverse. So again, basically what we do is we take that original and we kind of change it back out of function notation, and we'll just say E is equal to 4v squared. And so then we're just going to try to solve. We don't switch the variables again in this case because v and E are very specific to the situation, v meaning velocity and E meaning energy. So we're instead just going to solve. So I'm going to divide by 4 to get v all alone. And then I'm going to take the square root of both sides. So I take the square root of both sides, and now it's going to cancel out, well, I've canceled out the 4's already, it's going to cancel out the squared on the v, so that gives me v is equal to the square root of E over 4. And there again, that 4 is a perfect square, so if you want to go ahead and pull that out, you can. Sorry about that. And then to write it back into that function notation, it would be v of E. So in other words, velocity being a function of the energy in joules. So this is our function, and so now all we have to do is evaluate this v for 60 joules of energy. And so I'm going to plug in 60, and I'm going to divide by 4, and I'm going to take the square root, and that will tell me the velocity. And so I'm actually finding the square root of 60/4, which is 15, and that's approximately, and did it say how many units or how many decimals? I guess we'll go to the tenths. So that's 3.9, and that velocity was given in meters per second. So meters per second, 3.9 meters per second for that object with 60 joules of kinetic energy. So again, we're going to leave the your turn question for in class. So we'll go ahead and move on and take a look at some cubic and cube root functions. So next we're going to find and graph the inverse of a simple cubic function. So I just want to real quick remind you of the most basic parent cubic function. And so real quick I'll sketch that graph. So when we did a cubic function, again we're just taking different numbers and cubing them. And so y is equal to x cubed. And so some nice numbers that will kind of fit in our graph is if we kind of put in 0 and we cube it, we get 0. If we put in 1 and we cube it, we get 1. If we put in 2 and we cube it, we get 8. So it's got to go way up on the graph there. It's going to be right up there, about there. And so we've got, you know, a branch that almost looks like a parabola. But remember on the other side, we're going to be plugging in things like -1, and if we take -1 and we cube it, we'll get -1. And if we cube -2, we're going to get -8. Okay, so it's basically like a parabola where the one branch got tired, it just flipped down over the x-axis. So that's what your typical parent cubic function is. And so when we graph these things, sometimes we'll look at those and get those key points, that 1, 1, and -1, -1, and to kind of get that that bend or that kink point in the graph. So if you kind of recall when we graphed those. And so if I were to graph the function that's listed here, x cubed minus 9, it's basically like taking this graph here, this parent function, and it's just shifting it down 9, which is not really convenient with the graph that I have here. But anyway, so that point that's at 0, 0, that kink point is now at negative, or at 0, negative 9, so it's here. So then normally we would be going to the right and up 1 like that, and then to the left 1 and down 1, which of course is going to be off the graph here, but you can kind of get a sketch of it. And so what's really going to happen is it's going to look kind of like this. Then we'd go to the right 2 and up 8, so that would put us right here at negative 1. And then, so the graph would look like this. Oh, that was terrible, sorry. And it'll just kind of continue up and down along that trend. Down here it's going to curve down and go down forever. And remember that when you have cubic functions, there was no restriction on the domain or the range. It was all real numbers for both, and that's because it goes on the ends up and down forever, towards positive infinity and towards negative infinity, which also means we're not going to have to worry about any kind of restrictions on our cube root functions. Because you can cube root anything, positives, negatives, and whatever. And so if we wanted to now write the inverse of this, we could do, just like we did with the quadratics, we could replace f of x with y. And I guess I don't really know why I decided to do b first, but whatever. So now we're going to switch x and y so that we actually have x being equal to y cubed minus 9. And so then to solve, I'm going to get the y cubed by itself by adding 9, so that's x plus 9 equals y cubed. And then just like we can undo a square root, or a squared with a square root, we can undo a cube with a cube root. Okay, so we can cube root both sides, and then go back to function notation. We could say f inverse of x is equal to the cube root of x plus 9. Now in situations like this, I really, wouldn't be, upset if you used a graphing calculator to get points for this, because it is kind of like tricky to get nice points. So I already kind of ahead of time just kind of scoped out what numbers would be pretty easy to take cube roots of, and so I picked to plug in my table to graph this new inverse function. I picked to plug in negative 10, negative 8, negative 1. I even plugged in 0 just because 0 is a fairly easy number to put in, although it's not going to give us a nice number to cube root. So I just used these. So when I plugged in negative 10, because that's about as far as I could really get on this graph to fit because of the coordinate plane that we have, if I plug negative 10 in here, so that would be negative 10 plus 9, which is negative 1, and then the cube root of negative 1 is negative 1. If I plugged in negative 8 in there, negative 8 plus 9 is positive 1. The cube root of positive 1 is 1. And I guess I neglected, I forgot to put in here. Oops. I should have put in also negative 9. I'll put it down in here. Because if I put negative 9 in, that makes my radicand 0, and the cube root of 0 is 0. So that's actually was a really important point, so I messed up on that. Then if I put negative 1 in, so negative 1, where I plug that in, that would give me 8 for a radicand. Cube root of 8 is 2. And then if I just put 0 in, 0 would make that be 9 as a radicand. So the cube root of 9 is approximately 2.1. So that was probably not a smart one to put in. But anyway, so if I plot those points, I could plug in negative 10, negative 1. That's going to be, I'm going to just extend out my axis just a little bit. This was just kind of an inconvenient graph to pick. But so there's negative 8, negative 9, there's negative 10. So that point would be negative 10, negative 1, which would be right here. We've got negative 9, 0, which is right here. I've got negative 8 and 1. So that's like that, that kink point, and it's basically what's happening is that graph is turned to the side like that, and then at negative 1 it's 2, so that would be right here. And then at 0 it was a little bit higher, so just kind of telling you that that's kind of continuing to rise up a little bit, but very slowly. and you can extend that side out and this side out. And you can see, again, that what we're talking about are two graphs that are very clearly reflections of each other over the line y equals x, which is a visual way of verifying that they are inverses of each other. We could also do that composition of functions thing, so like I could plug one function into the other, like I could, in place of, say, this x cubed in the original, in place of that, I could plug in, oops, my stylus isn't working very good, I could plug in that cube root of x plus 9 in place of that x, oops, and then subtract 9, and then I'd see that that cube root and the cubing cancel each other out, leaving me with just this part right here, the x plus 9, but then you've got the minus 9 off the end, which is again leaving me with x, and I could go the opposite direction as well, and anytime I do the composition both directions and get just x, that means they're inverses of each other, they are undoing all of the operations of the other. We'll go ahead and look at one more. So example A is, again, we'll kind of write the inverse real quick. We know we don't have any restrictions. We know what the, well, actually we could real quickly figure out what the cubic function is to begin with, because normally we have a vertex at 0. Then we usually go right 1 and up 1, but now that's basically a vertical compression of a half. So instead of going up 1, we're going to go up a half, because 1 times a half is a half. So I'll have a point like right there. And then normally I would go to the left 1 and down 1, but I'll just go down a half. Normally I'd go 2 to the right and up 8, because 2 cubed is 8, but now I'm only going to go up half that amount, so that's at 4. So again, that's just like taking that cubic function and just kind of flatten it out a little bit. Instead of going negative 2 and down 8, I'm now going to go 2 to the left and down 4, because I'm only going to go down half that amount, so that puts that right here. And again, I got that graph. It's just a little bit flatter there. It's compressed some. And then to do the inverse, I got to write the inverse first. So I'm going to switch x and y, solve back for y. So I've got x equals 0.5y cubed. So I'm going to divide both sides by 0.5, which dividing by a half, which is what that really is like multiplying by 2. So I'm going to basically have 1 divided by 2 for my coefficient, or 1 divided by a half, which is 2. So that's 2x here equals y cubed, and then to undo that cube, I'm going to cube root it. So cube root both sides, and that leaves me with my final answer as y is equal to the cube root of 2x, but I'm going to write it in function notation, so that's f inverse of x equals the cube root of 2x. And then again, to graph it, I could just simply plug in some points that I know are, kind of work out kind of nice. And so I thought, well, let's see, I'll plug in 0, because plug 0 in, 0 times 2 is 0. Cube root of that is, of course, 0. So there's a point right there at 0, 0. If I plug in, say, a half, that might be a smart one to put in. So if I put in a half, then 2 times a half is 1. The cube root of 1 is 1. So I'll just go to the right 1 and up, go to the right a half and up 1, which would be right there. And then to the left a half would give me a negative 1 then, and so that would be right here. And then let's see, if I put in, say, 4, so plug in 4 for x, 2 times 4 is 8, the cube root of 8 is 2, so that would put me up here at 2, and that graph's going to go like that then. And if I put in negative 4, that gives me a radicand of negative 8, cube root of negative 8 is negative 4, so if I plug in negative 2, negative 4 and negative 2 would put me right there, and then that graph's going to turn that way. And then you definitely can see that reflection aspect of things here over that line y equals x. And so we're going to go ahead and end here, and we'll pick up where we leave off in class, and we'll continue on with the opportunity for you to try your turn questions, and also look at some applications with some of these cubic models and the inverses of cubic models. Thanks for coming to class.